Good morning, everyone. So we'll start back up here in Chapter 8 on Lewis structures this morning. So last time we were talking about nitrate. Let's actually start today with ICl4. This question is actually asking us to consider kind of comparing the oxidation numbers, the charges, and then even maybe thinking a little bit about how electronegativity might impact charges. So oxidation numbers just comes from Chapter 4. One of the connections to oxidation numbers would be that if we find an atom has a positive oxidation number, it should probably have a positive charge somewhere in the molecule, either through the actual formal charge assignment, or maybe through then thinking about how electronegativities impact charge. And so for ICl4, chlorine's the one that stays negative from oxidation number, so it would be -1, 4 of them, -4. So by oxidation number rules, iodine's oxidation number would be +3. So when all said and done, iodine should end up being the positive atom within this structure. So if we think about our Lewis structure rules, that's counting valence electrons. So 7 for iodine, 7 also for each of the chlorines. Negative charge, we add an electron into that valence shell. And again, we're counting the valence electrons, of course. Those are the ones we're showing in the Lewis structure. So we have 36 valence electrons to distribute. And then our basic rule is identify that central atom. It's usually not hard to identify the central atom. Here is the iodine, and then the chlorine's attached to that central iodine here. And then we complete the octets of the non-central atom. Then we count electrons. I've distributed 8 electrons per chlorine. There's 4 chlorines, so that's 32 electrons. The 4 electrons left over are placed onto the iodine central atom. Now, interestingly, if we calculate the formal charge of iodine here, it's probably not going to exactly be what we expected from oxidation number. The formal charge would go like this. Think about iodine on the periodic table or just as an ordinary atom. How many electrons should it have for a neutral charge? Another question is how many valence electrons does it have? That would be 7. So if iodine had 7 electrons, it would be neutral. If iodine had 8 valence electrons, it would be -1. If it had 6, it would be +3. And so then we try to figure out how many of these electrons are closer to iodine in the structure. So we break the bonds in half. So if I imagine breaking the bonds in half or drawing a box around iodine, I keep the non-bonding pairs on iodine, and I keep half the bonding pairs on iodine. And so I'm going to subtract the 4 non-bonding electrons and then the 4 bonding electrons, so that's -1. Iodine has 8 electrons closest to it within the Lewis structure, so it ends up with a -1 formal charge. So I might write like a little -1 for the iodine. The chlorines are all 0. They're all 7 - 7. And so they're all neutral. Generally, I don't write zeros all around the neutral charges, so I'll just leave those blank. But now you can think from formal charge being -1 for iodine, that doesn't make a whole lot of sense, right? Iodine is less electronegative, but 1 electron's less than chlorine. Well, how does chlorine respond here? Chlorine responds by trying to pull the bonding pair electrons closer towards itself. And the chlorines are going to pick up a partial negative. And I don't know this for sure, but I suspect they pick up such a high negative charge that that's going to end up pushing iodine to be positive. So if we put a 1/4 unit of charge on each of the iodines, that's a net -1. That would make iodine then turn neutral. If we make the chlorines a little bit more negative, that makes the iodine then go positive. So you can imagine the formal charge is like a Lewis structure, covalent bonds equally distributed between the atom charge. Then we can think, okay, let's undo that assumption and think about how the charges are going to then correspond in the real molecule to then reflecting probably their true charges, chlorine being negative and iodine probably flipping over to being partially positive. Okay, so we see the charges from the oxidation numbers don't bear out. We're rarely ever going to see that except for in actual ionic compounds, but at least we're able to predict which atom should end up with the positive versus negative charge from inspecting oxidation numbers. Let's look at SO3 2-. -2 for O for just the oxidation number. So -6 for the collection of 3 oxygens. So that makes sulfur +4. So sulfur should end up with some kind of positive charge when all said and done within a structure for sulfite ion. I'm going to erase this math here. Let me think about the valence electron count for sulfur. It's in the oxygen group, so that's 6. 3 times 6 for the O's, +2 for the negative charge. So that is 26 electrons. And so then central sulfur, attach the 3 oxygens to it, complete their octets. That's 8 per O. The 2 unassigned electrons can be placed onto the next spot where there's room for electrons. That would be on the sulfur atom on the central atom. And so now this is actually an interesting kind of point here for our Lewis structure. We have sulfur satisfying the octet role. If we think of the octet role would be consider all of these electrons surrounding a given atom. So the octet role would be, consider all these electrons here and count them up. So we'd have, 2, 4, 6, 8. That's good for most atoms or some molecules head towards this octet role. Now let's think about the charge of sulfur here. The formal charge should have 6 electrons for neutral charge. We only have 5 electrons around that sulfur. We have the 1, 2, 3, 4, 5 electrons here. So that results in a net positive charge. So if we have a positive charge, can we expand our octet? Now, expanding octets is kind of peculiar. We have a rule that we outlined last time. We'll look at it again for nitrate again here today to make sure we see the distinction. But for second row atoms, there's no expanding octets kind of period. Like by rule, we're not going to expand the octet if we have like a central nitrogen atom. In fact, let's go ahead and jump into nitrate and kind of show this corollary here. So 5 plus 3 times 6 plus 1 for nitrate. So that's 24 valence electrons. And so we ended up with the structure last time where we started just like for sulfite with this structure here. And then here we should have 5 electrons around the central nitrogen. We only have 3. So that's a +2 formal charge. We have minus oxygens. The oxygens are 6 minus 7 electrons right now for -1. And so for nitrogen, we had what I would call room for electrons. We have an open octet, still we haven't filled the octet. And we have a charge. Electrons are negatively charged, so it seems like this positive charge here ought to be able to pull an electron pair into that spot here to make a double bond. So we make a double bond between the N and the O. We lose the electron pair on the O because it's moved in to make that double bond. And then we change the formal charge. And so our formal charge now on nitrogen is 5 minus 4 for +1. Okay, and so then the charge on this oxygen drops to 0, 6 minus 6, and the other oxygens, of course, remain minus. And so now for nitrate, if we're thinking, okay, we still have a positive charge, electrons are still negatively charged, why don't we do this? So can we do this? Can we make that second double bond? And at first glance, you would think, well, why not? Because this reduces the magnitude of formal charge. Remember, the idea of multiple bonding is if you can reduce the magnitudes of formal charge, then let's make multiple bonds. Well, not if we have to expand the octet of an atom that can't expand its octet. And so we can't do this because we cannot expand the octet. So you cannot expand the octet of second row atoms. Now, to be fair, in this case for sulfite, I don't think you really can either, but the book is a little wishy-washy on this, so let's talk about what the book talks about. For sulfur now being in the third row, sulfur can expand octet. We saw last time, like SF4, SF6 have expanded octets in their Lewis structures with single bonds, but they still have expanded octets. So why don't we go ahead and make this double bond here for sulfite. Let me erase my formal charge calculation here and write that Lewis structure where we have S double bond O, and then the oxygens here still have a lone pair on sulfur. So I've just made one double bond, and then the other oxygens remain as they were with 3 pairs of electrons around each. And now my formal charge magnitudes have dropped for the O and the S involved in that double bond. And so that's good. If we're making multiple bonds, we have to reduce the magnitudes of formal charge. We can't increase the magnitude. Like BF3, if you remember last time, we tried to make a double bond to satisfy an octet for boron, and we were like increasing its charge, which was a bad idea, and we didn't do that. And so for SO3, we actually can do this if we want to satisfy the so-called formal charge rule for an atom that's allowed to expand its octet. And so we would call this structure here like the formal charge rule Lewis structure. And so the formal charge rule being satisfied would be, this would be the best Lewis structure that minimizes the magnitudes of formal charge, even though it expands the octet. And then the Lewis structure here, the first one we started with, would be the octet rule Lewis structure. And now the book makes a claim somewhere, well, it seems like computational theory or quantum theory seems to suggest the octet rule structure is probably the more realistic one, the one that really is probably better describing the sulfide ion. But it continues to show, well, but we can write these Lewis structures that satisfy the so-called or alleged formal charge rule, where we're minimizing the magnitudes of formal charge. So we end up with 2 Lewis structures that we would say are acceptable Lewis structures for something like sulfite. We would just say, in some questions you'll see on practice exams, we'll say, for sulfite, give us the Lewis structure that satisfies the octet rule for all atoms. And then you would go with this Lewis structure. And then we might say, well, show us the Lewis structure for sulfite that minimizes the magnitudes of formal charge, and then you'd go with the structure that looks like the bottom structure. But now we have another complicated topic to get into, which is how structures actually resonate double bonds. So a thing called resonance ends up kicking in for nitrate, for sulfite as well, if we want to think about that double bonded structure, where that Lewis structure is actually not something that ever really represents what the molecule looks like. This gets a little complicated. Let me show this slide here to talk about nitrate a little bit. So if you think about nitrate having what we would refer to as like a localized double bond. A localized double bond just means it's exactly where you're sketching it. So a localized double bond would mean we have a double bond specifically right here, and then we have these other O's over here. And so the issue for nitrate, and for a lot of molecules like it that have these double bonds where we could have sketched or moved the double bond somewhere else in the structure, like we could imagine moving the double bond over to here, and then we return this oxygen back to the -1 formal charge, and we make our double bond over here. And then you can also imagine moving the double bond over to here. So it leads to the question of what does the double bond really do? Does it go from here to here to here and it's going back and forth at all times? Well, if we look at the orbital structure of nitrate, we'll see this. This is actually chapter 9 picture. But what ends up happening is you end up having these orbitals all sticking up in the same direction, and that extra double bond can spread itself out across all of those bonds simultaneously. So that it really never, the molecule nitrate really never is here, it's never here, it's never there, even though we can sketch those 3 Lewis structures. Okay, so if hopefully I'm not losing too many people here, but the idea of Lewis structures, if you go back to the beginning, is they're a model to try to understand what molecules might look like. They aren't the model. They aren't exactly the representation of molecules. They're helping us understand how molecules behave. What we're seeing here is that resonance is going to kick in, and that the double bond, that extra double bond, is always going to distribute across all 3 atoms simultaneously. And the molecule is going to exist as the composite. So resonance leads to, and that's really what the word means, the electron pair is resonating at all times across all three of those bonds. So that's a resonating effect of that electron pair. So it's not an equilibrium. It's not a here to here to here, back and forth. It's just always a spreading out of that charge across the molecule. So when we look at nitrate, if I think back and I just resketch a Lewis structure here, and then for anything like it, where the question would be, can I write equivalent yet different Lewis structures? And I have the other equivalent yet different Lewis structures that we can write here. So I have the three different Lewis structures that are equivalent in what they're representing. They each have one double bond, two single bonds. Then we're going to have this effect of resonating bonds. And so I look at these three bonds and think, okay, it's really going to resonate. So when I look at the bond, it's going to resonate across all three centers. And I'm going to have 4 bonding pairs of electrons in total. So the 3 bonding pairs for the single bonds plus the extra double. So I have those 4 bonding pairs of electrons being spread across the 3 NO bonds. So I have like a 4/3 bond here. So I end up with like a 4/3 bond order. If you start thinking bond order as a single bond is 1, if you think nitrogen double bond order here would be 2. So that's the bond order, is what the bond order is standing for. So a double bond has a bond order of 2. So a bond order of 2 just means you have 2 pairs of electrons spread across the one bond, is the idea of bond order. Single bond has 1 pair of electrons across the one bond. And then we're saying here for nitrate that this bond order would be about 4/3. Because we're just spreading that extra double bond across those 3 NO bonds simultaneously. So you'll see a lot of questions on practice exams, practice quizzes, real exam later that kind of get into, is this a back and forth? It's not a back and forth. Is this an equilibrium between these different Lewis structures? It's not an equilibrium. It's an always spreading out the charge across those 3 centers. Let's look at a couple other examples. Ozone does this. Ozone's an interesting molecule. It's an allotrope of oxygen. It's lesser stable than oxygen. If it was more stable, we'd probably be breathing it in. It's actually toxic, so that's probably good that we're not breathing it in. It is an important component of the atmosphere because it filters out UV rays. So the ozone layer is important in the atmosphere. So it's an important molecule in a lot of different ways. The 3 oxygens just have to be connected in linear sequence, right? There's no other way to connect 3 oxygens. So we have 3 oxygens connected together. If you think of our usual rules for Lewis structures, we're just connecting the non-central atoms with their octets. We have 3 times 6 electrons to distribute through, so 18 valence electrons. And so I've assigned 16, so I have 2 left over. So we can put them on the oxygen, the central oxygen. And so then at this point here, our formal charge would be 2+ for that oxygen. 6 should have 6, only has 4 electrons surrounding it. So I have charge, I have room for another double bond. So I make a double bond here, lose that electron pair there. And then I reduce the formal charge, magnitude down now just a plus. And then the other oxygen being negative. So hopefully the formal charge is here, so the first one 6 minus 6. 6 minus 5, and then 6 minus 7 for those formal charges. And then we have the same issue of resonance. So I have the same issue where I can make the double bond with the other O and have the double bond moved over to the other oxygen. And so then as soon as I notice that I have these 2 resonance structures, that ozone can't exist as either one of them. So ozone, if we think of one being A and the other being B, ozone's never A, it's never B. And it's confusing at first because it's like, well, then why did I write A? Why did I write B? Well, the Lewis structure rules led me to writing A. Then just the simple geometry of the molecule leads me to see that I could have sketched it as B, meaning I could have made the other double bond with the other O. Then I have to think the real molecule is going to average this out. So if we look at ozone, like a charge distribution diagram of ozone, we see the two O's look identical on the outside. The non-central atom O's have the same charge as each other. It's not that one is minus, the other is 0, and then they flip back and forth or anything like that. It's just like they always spread out that double bond. So the real molecule of ozone would kind of look more like this. So if we wanted to describe the bond order of ozone, how might we describe it? Like before we had nitrate was a 4/3 bond order. What do you guys think here? So we have 1, 2, 3 bonds being shared. So we have 3 bonding pairs of electrons spread across the 2 OO bonds. So it's kind of right in between being a single versus a double. So that would be a 3/2 bond. The next question will have us think about bond length, and I think it's exactly what you might expect. But notice the two oxygens' charges look identical. The charge on the O's in terms of a formal charge, if you notice, we're alternating in our Lewis structures between -1 and 0, and for the other one, of course, -1 and 0 as well. And so the average charge of the O's we can see from the two Lewis structures would be -1/2. So we look at this O here and see it's either -1 or it's 0. Those are the two possibilities. So the charge on that O would be about -1/2, and that's its formal charge. So we're just averaging out those two formal charges. If we think back to nitrate for a minute and just say, okay, let's look back at nitrate. This is one of its Lewis structures we sketched. So here our O's are either 0, and if we think of the other two Lewis structures, then that other O, that 0, would be minus and minus. So if we're thinking of the average charge in nitrate, so if we want to think of what the charge of the O might be for nitrate, where we're imagining this spreading out of the electrons, so we're 0, -1, or -1, 3 possibilities, -2/3. So each of those O's are about -2/3 formal charge. So we can even imagine the charge of the O's balances out at all times through the resonating effect of that electron pair. So about -1/2 for ozone, -4/3 or -2/3 for nitrate, and then again the bond order, 4 bonding pairs across 3 bonds. That's how we're thinking of the bond order. Let's think about benzene. This actually comes up a little bit more in chapter 9 too, so some of these terms we'll see again or can hopefully reinforce in chapter 9. But benzene is an important organic molecule that has this resonance issue going on, because benzene, which is the structural formula C6H6, we can imagine these double bonds moving in the Lewis structure, and then you end up with like an A and B situation where A and B are exactly the same. Not exactly the same, that's the wrong word. They're equivalent, but they're still different from each other. They're equivalent in that they each have 3 carbon-carbon double bonds. The other carbon-carbon bonds are single, and but they're different in the regard of which carbons are making the double bonds. So the important word here might be equivalent yet different. So we have equivalent yet different Lewis structures. That's where we lead to the effect of resonance. The effect of resonance leads those bonds to become the same type of bond. In fact, ozone, I don't know if this is obvious, this should be obvious, hopefully it's obvious, that in nitrate and ozone, because they have the same bond order, they're both like 3/2 in ozone, 4/3 in nitrate, the bonds have the same length, right? That's the idea here, is that nitrate's bonds would all have the same length as each other. Ozone's bonds would all have the same length. So nitrate and ozone, all their bonds are the same length. So we we have the same length bonds. And so the 2 bonds in ozone have the same length. The 3 bonds in nitrate have the same length as each other. Now, all of the carbon-carbon bonds in benzene have to have the same length. So we look at these 3 bonds here. It's either double or single. These average out to be 1.5 bonds, right? So we're just sharing the 3 bonds across the 2 carbon-carbon bonds. If you think of the entire molecule, if we want to say, well, what about the entire molecule? Hopefully we can see that we're taking 1, 2, 3, 4, 5, 6, 7, 8, 9 bonding pairs on those carbon-carbon bonds and spreading them across the 1, 2, 3, 4, 5, 6 carbon-carbon bonds. And I think it's really obvious, right? It's either double or single, so it averages out to 1.5. So these are 3 halves bonds or 1.5 bond order. So benzene has 2 of these resonance structures. The average bond order of the carbon-carbon bond should be 1.5. So never double, never single, they're always 1.5. And that equalizes all the carbon-carbon bonds to have the same length. So all the carbon-carbon bonds should be equal in length. And if we're thinking like a carbon-carbon bond should be longer than a carbon-carbon double bond, remember how we were thinking more bonding pairs shortens bonds, so that this 1.5 bond will be somewhere in the middle. So if our carbon single bond is long, double bond is short, the 1.5 is somewhere in the middle. And then this is like a weird question. We'll see this maybe develop a little bit more, but there's like a pi system, that, just like there is in nitrate. We're going to see that there's a set of pi orbitals on each of these carbon atoms that all overlap with each other. And then they take those double bonding pairs of electrons. So the double bond's the extra bond. They're taking that extra bond. And so we're going to see that we end up with the 3 double bonds. Those electrons would be 6 electrons. So we end up with those 6 electrons in this, what we call pi system. And the pi system is what's leading to the resonance. So the pi system is the system of orbitals that's like sharing those electrons simultaneously, that's allowing those bonds to resonate across the molecule simultaneously. And so we'll revisit that when we get to chapter 9. So we'll see a better picture of benzene once we get sort of a picture of what its orbitals might look like. Now let's return to sulfite. When we were looking at sulfite, we had this Lewis structure for one of the formal charge rule Lewis structures. We had a lone pair on sulfur. Now for this structure here, like you could equally have sketched the other 3 resonance structures. So we can move the double bond over to here, kick the double bond back to single here. So we go minus, minus, 0, lone pair on sulfur still. And so here we were starting minus, minus, 0. And then we can have the other possibility being over to here. So this being 0, minus, minus. And so the bonds are going to equalize here too. So we're going to look at this structure here and see that resonance should be going on. The structure should look more like this. Bond order is pretty obvious, the same as nitrate, right? The bond order is going to still be 4/3, like nitrate. So these bonds here, 4 pairs of electrons. So 1, 2, 3, 4 pairs of electrons spread across the 3 SO bonds. So here we're thinking bonding pairs. And here we're thinking chemical bonds. The charge of the O is just like nitrate. The charge of the O is -1, or 0. So our charges on O, -2/3. Now, a common question you'll see will say something like this. Imagine, this Lewis structure here. Imagine this Lewis structure for a molecule. Is one of the bonds in sulfite shorter than the other two? What do you guys think? Does anybody think one of the bonds in sulfite is shorter than the other two? None of the bonds in sulfite are shorter than the other two. All three bonds are equal in length. Okay, so we have to imagine if we see just one Lewis structure, maybe we have to understand there'd be two other resonance structures, and resonance kicks in, resonates that electron pair, and all those bonds end up having the exact same length as each other. Okay, so it's not an equilibrium effect. It's not a back and forth A to B to C effect. It's a spreading out effect at all times that leads to this resonating effect, and all those bonds have an equal length. Okay, so for O2, hydrogen peroxide, ozone, can we rank their bonds in order? So this will just give us the reminder that oxygen's a double bond, only has 6 electrons each for each of the O's. That's 12 electrons. And so hopefully that's a pretty obvious Lewis structure. So that's our double bond. Ozone next will probably, if we just thinking these in terms of bond order, ozone was the one with the double bond here, where we have the resonance effect going on. So even if we don't sketch both Lewis structures, even if we don't sketch the averaging, we can imagine that this has to average over to here. So my bond order for ozone ends up being 3 halves, with both bonds being equal in length. And that this bond compared to the double bond should be longer. So there's fewer electron pairs being shared between the atoms. And then hydrogen peroxide. Now, hydrogen doesn't bridge. So sometimes you see H2O2, you might be a little confused on how these atoms might be connected, but these just connect by H to O to H. And then if we think of our Lewis structure rules, we have 2 for the H's plus 2 times 6 for the oxygens. That's 14 total electrons. We've assigned 6 electrons so far. So there's 8 electrons left over. So I just put 4 onto each O. We could have also maybe done a dot structure. So this, maybe you're thinking, well, why aren't we just starting with this and then connecting another O here and then connecting an H here? So there's a couple ways you can arrive at that hydrogen peroxide Lewis structure. But the key would be that oxygen has a single bond. And so the single bonded O, even longer than the bond in ozone. I meant to look these up, but if you're ever curious, you could probably just Google the bond length of I think you put hydrogen peroxide into Wikipedia, it'll show you its bond length, same thing with ozone. If you want to see that there's going to be a trend that should follow this prediction here, that the double bond shortest, the single bond the longest, and ozone in the middle. All right, so for sulfate, let me actually give you guys this question here. So try to sketch the Lewis structure for sulfate. It actually doesn't matter which Lewis structure you go with, the octet rule Lewis structure or the one that, that minimizes formal charges. It shouldn't actually make a difference here, and see if you can correctly answer this question. So I'll give you guys 2 or 3 minutes on this. Does anybody think the answer is C? Good, because the answer is not C. The answer would be, of course, A, right? So all of its bonds are going to be equal in length. And it doesn't matter, actually, which of the Lewis structures you go with. So the octet rule Lewis structure, I think, is probably, though, the clearest. That you can clearly see that all the bonds are single bonds, and they all are identical in bond order, so they have to be identical in length. But if we want to go with the formal charge rule Lewis structure, where we minimize the magnitudes of formal charge, we make 2 double bonds. We don't make 4 because that would make sulfur -2. We stop when sulfur hits 0. We want to minimize the magnitudes of charge down to 0. We can do so by making 2 double bonds, but then we can resonate those double bonds across the molecule. I think there's 5, or all the permutations of moving the double bonds across to have 2 double bonds and then 2 single bonds across the molecule. And so that resonating effect is going to equalize all those bonds to being of an order. What bond order would we expect here? What do you guys think? So the bond order, I would have 2 doubles, so that's 1, 2, 3, 4 pairs, and then 5, 6 pairs of electrons total, spread across the 4 SO bonds. I think they look like 3/2 bonds, but you can calculate that just by taking, there's 6 total bonds between the S and the O's, 2 sets of doubles, 2 sets of singles, and so that gives us a bond order of 3/2. But they're all the same. That's the idea here, is that all those bonds would have the same length as each other. I think sulfate's better described with single bonds, but the book does describe both structures. So if we just wanted you to give the proper Lewis structure, for sulfate we would say give us a Lewis structure where it minimizes magnitudes of formal charge. We'd expect something like this. We'd still expect you to understand resonance and all the bonds have the same length. Or if we say which one satisfies the octet rule, then we'd go with the structure with 4 single bonds. Now I just want to make sure that we understand what a localized versus a delocalized, like the bonding in sulfate with the formal charge Lewis structure, nitrate, ozone, benzene, those are showing what we call delocalized bonding. So where you delocalize a bond is where you move it through the structure. That's what something like carbonate we'll see is doing. So carbonate is 4 plus 3 times 6 plus 2. So that's 24 electrons. So for carbonate, kind of just like nitrate, we'll start with this Lewis structure here. By rule, we have the positive charge on carbon, so we make 1 double bond. And then we stop at 1 double bond because carbon's charge is 0 now. And then our charges are minus and minus on those 2 O's, 0 for the one with the double bond. And so here we have the effect of resonance. So we have the resonating double bond, and that's delocalization. So that's that bond delocalizing across more than one bonding center, or more than one bond. And so we have that delocalization take place. So carbonate has 1 delocalized bond. So that double bond delocalizes across three of the carbonate bonds. But then a localized bond is exactly where you think it is. So like in formaldehyde, CH2O, so we have carbon, 2 hydrogens, and oxygen. If we wanted to start with the usual, give the non-central an octet, count our electrons used, 2 for the hydrogens, plus 4 for carbon, plus 6 for O, is 12 total valence electrons. I've distributed 2, 4, 6, 8, 10, 12. And so, but I have a positive charge, so let's make a double bond. So we make our double bond, reduce our charge magnitude down to 0. And so this is a structure, and I just want to make sure we see the word localized. A localized bond is exactly where you think it is. Like there's nothing silly going on here. This bond isn't moving over to here or any of that business. So that bond is exactly where we think it is. So formaldehyde has a localized double bond. So localized just means it's exactly where you're sketching it within one Lewis structure. There's no other Lewis structures that are equivalent yet different. And then OF2 is just a distractor here. We might recall that it had this structure that looked like this. if we count the electrons, 14 for the Fs, oxygen was 6, so that's 20. We've distributed 16 by the usual rule so far, so 4 electrons onto the central O. So no double bond in OF2. I don't think we really intend for you to memorize Lewis structures, but you probably will from time to time. Just do a Lewis structure a couple times and come to memorize it. If you had remembered that this didn't have a double bond, that's fair. You don't, like carbon dioxide, for example, I know that it's this, and you guys might know it's that too. If we know the Lewis structure, I don't need to bother with the rules and going through and structuring it. Or maybe I do just to make sure I can see how the rules get me to that Lewis structure. But if you know a Lewis structure, you can certainly, you may have known that OF2 wasn't a molecule that had a double bond. All right, so let's talk about when we have some molecules like the hydroxyl radical, NO without a charge, CLO, no charge. These molecules are what we call radicals. They have an odd electron count. So one of the atoms has to sort of violate the octet rule due to having that odd electron count. So for hydroxyl, we have 6 electrons plus 1 is only 7 electrons total. 5 plus 6 for NO, that's 11. And then CLO, 7 plus 6, that's 13 electrons. And so I think the easiest way to get these Lewis structures correct is to kind of imagine their negative ions first. So if you imagine OH with a negative charge, then that would be 6 plus 1 for 8. And then this is really an easy Lewis structure, just oxygen, hydrogen, and then there's the 8 electrons. And then for the radical, if we want to kick an electron off, we want to get rid of that minus charge, so we have to lose an electron. Well, there's really any of the ones on O to choose from. We're not going to remove the bonding pair electron because that would probably break the bond. So we end with the Lewis structure for hydroxyl that looks like this. So if we imagine NO with a minus charge, which we had previously sketched a Lewis structure of, this has 12 electrons, one more than NO without the negative charge. And so this one was just like O2, where we had the double bond. So this might be NO minus. If we want to kick the electron off, now we have a question. Where do we want to kick the electron off from, the N or the O? And so let's sketch the two possibilities. So maybe I remove an electron from N, or we'll remove it from the O. So the question would be, which one of those structures is better than the other? This is really where the formal charge rule kicks in. So in a formal charge rule, when we're choosing between Lewis structures, that everything else is equivalent. So one double bond, same electron count, just a matter of where we're putting the charge. We want to choose the structure with the lowest magnitudes of formal charge. So we look at the first structure. Nitrogen's 5 minus 5, that's 0. Oxygen 6 minus 6, that's 0. And if we look at the second structure, notice how this probably doesn't look as good. Nitrogen's 5 minus 6, that's minus 1. And oxygen is 6 minus 5. That's plus 1. And so it's not even necessarily about putting the charge on the wrong spot. It's about maximizing the charge versus minimizing the charge. We want to minimize magnitudes of charge when we can do so within a Lewis structure. So our Lewis structure should show the charges minimized as 0 and 0. So even if you imagine the negative charge end up on O and the plus on N, which would be better, right, because oxygen is more or less negative, that's still technically bad here. We want to minimize magnitudes of charge when we're choosing between alternate Lewis structures. For CLO, again, maybe go to CLO minus with 14 electrons. And then just choose the atom we're going to kick the electron off of. So if we want to remove this electron, we have to remove an electron. So let's remove one off chlorine or remove one off the oxygen atom. Which one do we think is better? The chlorine structure should have 7 electrons surrounding it. I have 1, 2, 3, 4, 5, 6. So that's positive. And then oxygen should have 6. Now it has 7. Now, at first glance, you might think that's good, but it's actually not as good as the structure below where we have 7 minus 7 for chlorine. for 0, and then 6 minus 6 for oxygen for 0. So we want to minimize the magnitudes of formal charge when possible. So we go with the CLO with the electron removed from oxygen. And I just want to make sure we see that, you might be looking here and saying, but isn't that a good thing that oxygen was negative? Well, it's not necessarily as good as just minimizing the magnitudes of formal charge. And then you can maybe say, break the formal charge. So if we start with 0 and 0, and we then say that bond should be polarized towards O, that lets us think oxygen probably has some partial negative charge on it. I bet it's not quite -1, though. And so do you see how this Lewis structure here might be making us think oxygen is actually probably more than -1? If we thought that this structure here was the Lewis structure, we would probably think the bond polarity would make oxygen even more negative. When oxygen probably starts closer to 0, then the bond polarity kicks it to be a little bit partial negative, but it's probably not quite -1. If we got its bond length and its dipole moment, we could calculate it. It'd be an interesting problem, but I bet it's not quite -1. I bet it's nowhere near even like half a negative charge. Maybe we'll do this review problem later just to see what it is and to go through that analogy. But we minimize magnitudes of formal charge when possible when we're evaluating Lewis structures that in all other ways are equivalent. Being lower in formal charge is better. Now, some molecules violate the octet rule. We've already talked about BF3, and it was perfectly happy being single bonded to the fluorines. So that's fine here. Nothing wrong with this Lewis structure. In fact, you can imagine boron is kind of like aluminum. Like we're almost ionic here. Like if boron was a little bit less electronegative, this just would have been B3 plus F3 minus, and this would be kind of like aluminum chloride as an ionic compound. Beryllium the same way, where we form beryllium to fluorine. And beryllium is like magnesium, almost a metal. It's a metalloid, so it's kind of behaving like a metal and non-metal. So we end up with beryllium here sharing electrons with fluorine, being deficient of an octet, and that's perfectly fine. In fact, fluorine in these compounds is pulling electrons closer towards itself, picking up a partial negative. So beryllium F2, it's kind of like magnesium F2 would just be magnesium 2 plus F minus, because we have a big enough electronegativity difference, and you have metal, non-metal. Here you have metalloid, non-metal, making a covalent bond that is just polarized, where the fluorine's adopting these partial negatives. So we can break the octet rule by having an expanded octet. We saw it previously for like sulfur atoms. Third row and beyond can do that. We can have a minimized octet. We see beryllium and boron are good examples of this. If you go down their rows, you just end up getting towards metal complexes. So like aluminum chloride would just be ionic. Magnesium fluoride and chloride would be ionic. So once you get to other atoms in their rows in the periodic table, those would just be ordinary ionic compounds at that point. And then we see some atoms violate the octet rule by having an odd count. So maybe I didn't stress this, but this oxygen here, like in CLO, doesn't have 8 electrons surrounding it. So the electron without the full electron pair that has that one electron that's spin unpaired would be deficient of an octet. So like in hydroxyl radical, this oxygen here only has 7 electrons surrounding it, not 8. So that oxygen is deficient of an octet, and that's perfectly fine. There's really no other choice for that molecule, but it is a molecule that does exist, so it's important to think about its structure. All right, let's think of a couple more Lewis structures here. So like NCO minus, like whenever you see a structure like this, I mean, we're literally intending that it's N to C to O is the connection. That if it were C to N to O, we would have written it CNO. So whenever you see a compound kind of written in a particular order, we're really meaning that the atoms are connected linearly in that fashion. So we have N to C to O. If we think of our usual Lewis structure rule, we're probably doing lone pairs in the non-central. We have a total of 16 electrons. So I have assigned 16. So now I have a 2 plus charge on carbon. So the question would be, well, where do I make the double bonds from here? Because I'm going to want to make one double bond here, kick that charge down to plus. At this point here, I'd have nitrogen 1, 2, 3, 4, 5, 6 for -1. I'd have this oxygen -1. And so now, do I make the double bond here? go to this structure, which would make oxygen 0, nitrogen stay -1, internal carbon 0? Or do I do the double bond over here? Do I move this electron pair in, make a triple bond, leave the other oxygen single? So if I call this one A and this one B, which one looks better? I think B looks better because here now I'm evaluating 0 versus -1 or -1 versus 0. If I could have the negative charge on the more electronegative atom, that's good. But notice that there was no 0, 0 choice. Like there was a 0, 0 choice in the CLO example on the previous slide where we had -1, +1, 0, 0. So 0, 0 is better than minus, plus, no matter where the minus and pluses are. And here it's not 0, 0 versus minus plus. This is minus here versus minus there. We would prefer the negative charge be on the more electronegative atom when all else is equal. So we go with a triple bond between N and O and a single bond between C and O. Now, again, you might think, well, why don't we do this and just get rid of that charge? But that would make carbon negative, so we don't do another double bond. So, and then also carbon can't expand its octet either. Now, N2O is nitrous oxide, and so N's the central atom here, so we have a central N with a nitrogen on one side, oxygen on the other, much like the example above. In fact, it has the same electron count of 16 total. So we end up in the same type of Lewis structure scenario as above, where we have now a 3+ charge on nitrogen. We make a double bond, and then we're going to make another triple bond here. So we've lost these electrons here. We now have a 0 for the nitrogen on the end. The nitrogen in the middle should have 5, but only has 4, so it's positive. And then our oxygen is minus, 4 mole charged. And if we thought about this one here, you might think double bond here to minimize the magnitudes of charge. Why don't we do that, though? We can't expand the octet of nitrogen. So we can't make another double bond here. Nitrogen's stuck with 8 electrons surrounding it as its maximum. And so this would be our best Lewis structure for N2O. That's a good way to get me to end, I think. Somebody's alarm go off. We'll pick up with these examples here. I just want to remind myself of, and maybe even you guys, the next couple slides is just a periodic table, so that's just if we did one. So we'll get into some bond strengths next time. This problem here, though, we've actually already solved this in Chapter 5, so we don't need to go back through problems that look like this one here. So this was a Chapter 5 problem, so we're going to skip this problem. And we just have a couple more sheets to get through in Chapter 8, maybe do a review problem or two, then we'll head into Chapter 9 on Monday. Have a great weekend, everybody.